And now let's start with the next session on multimodal journey planning. So what have we seen so far? We've looked at road networks, and the foundation for the algorithms we saw for those was Dijkstra's algorithm. We saw that pre-processing techniques enable interactive queries with running times of less than 1 millisecond, even on continental sized graphs. For public transit, we saw that algorithms tailored to the specific structure of the timetable outperformed Dijkstra's algorithm. We looked at multi-criteria optimization. We saw that optimizing arrival time alone is not enough. And we looked at criteria like number of transfers. I don't think we actually saw walking time in the last session, but we will be looking at that now. And we looked at fare. And some algorithms like Raptor and connection scan support footpaths, but only in a limited capacity. And I didn't mention it specifically for Raptor, but the same limitation is true for Raptor that we discussed for connection scan, that the footpath graph has to be transitively closed. Okay, so now we want to look at multimodal queries. We want to combine multiple modes of transportation, including both timetable-based ones and road-based ones. And we want to support queries between arbitrary endpoints in a mixed network that combines multiple transportation modes. Let's look at the transportation modes that we might want to consider. So on the one hand, we have public transit, which for our purposes includes all schedule-based modes of transport. I know that there are some more esoteric cases of transportation modes that you might call public transit, even though they're not schedule-based, because they might be on demand. But for now, we will call everything that is schedule-based public transit, and everything else we will deal with in a different manner. So we have trains, trams, buses. We might also want to consider flights. And then on the non-schedule-based side, whoops, that went a bit too far. On the non-schedule-based side, we have everything that we can model with road networks, which includes walking, bicycles, e-scooters, private cars, at least for the first and final leg of a journey, taxis, and also bike and car sharing solutions. So let's look at what is done in practice. Most production systems that claim to support multimodal journey planning in fact use heuristics, and that includes Google Transit or Deutsche Bahn. And usually multimodal means that they support public transit, which, as we saw in the last session, only includes a few predefined transfer edges between stops that are close by, and then they add some limited initial and final walking on top of that to get from your source location to the first stop and from the final stop to your target location. And limited means that there might be a hard cap on the walking time, such as 15 minutes. And to make matters worse, though that initial and final walking is often computed with Dijkstra's algorithm, so the whole thing is pretty slow. So that isn't satisfactory for a number of reasons. First of all, what if there's a good solution that requires 15 minutes and 1 second of walking, which, depending on where you start your journey, might not be that unrealistic? And what if you're using other non-schedule based modes that are faster than walking, such as e-scooters or even taxis? Because a limit of 15 minutes on walking, that gives you a fairly small radius in the network. But if you do the same thing with taxis, of course, with a taxi, you can get quite far in 15 minutes. So that will make the whole thing more expensive and makes it even slower, or you might have to lower the radius that you consider. But of course, if you allow for a 3-minute car drive at the beginning of the journey, you might as well skip that mode altogether. And finally, we only allow a few predefined transfer edges in public transit, and that usually means stuff like if you have a train station and you have a bus station right in front of the train station, then you might have a transfer edge connecting those two. But even things like having a bus station and a tram station which are around the corner from each other, often not even those will be connected with a transfer edge in many real production systems. And if you get into transfers that are longer than that, let's say you might have something like 10 minutes of walking between stations, most systems don't consider that. So what we want is we want to combine as many modes as possible, including non-schedule based modes. We don't want to limit their use from the algorithmic side. So obviously we're going to be running into problems later where if we allow unlimited use of certain modes, we might get journeys that consist of 5 hours of walking, but we can handle that if we carefully choose the optimization criteria that we're looking at. But we want to at least start with technically unlimited use of all transportation modes, and then we want to filter out solutions that aren't realistic afterwards. And the journeys that we obtain, we want them to be provably optimal. All right, let me give you a quick overview of how you would solve this problem with a graph-based approach, and then we're going to be switching to more timetable-based approaches in a minute. But for the moment, let's say that we model everything as a graph, including not only the road networks, but also the public transit networks. So we use a graph-based public transit model. And for each transport mode, we have one subgraph representing that mode. And now we have to connect these subgraphs with link edges at the appropriate locations. So we might have a node from the rail network over here, another node from the road network, and maybe it's an airport, so we have a flight network as well. And now we have to link all of these somehow so that you can transfer from one subnetwork into the other. Usually what we do is, if we don't have any more precise information, we will connect vertices with their geometric nearest neighbor. So we take the rail node and then we match it with a road network and we find the nearest neighbor, and then we add a link edge between the two. If we have more specific information, for example, considering indoor routing, that's even better, but usually we can do pretty well by just matching nearest neighbors and inserting link edges between them. And then we have to label each edge with its transportation mode. So this edge is labeled link. This from the rail network, these edges would be labeled rail. And here we have a road network. And now we can apply Dijkstra's algorithm on this graph, and this will give us the fastest journey using any kind of modal combination that you would that is possible. Just as a small aside, of course, if you allow any kind of modal combination, and let's say you have walking in there and you have taxi in there, and the only thing you're looking at is computing the fastest journey, then you won't be surprised at what happens, which is that taxi always wins because it's faster. So you do have to take care to either to choose your optimization criteria carefully. So if you include taxi, you should include some way to measure the fare of the taxis, because otherwise, because it's the fastest mode, it will always win. And you also run into problems like you might get modal combinations that aren't actually feasible in practice. So you might have a train segment followed by a car segment and then another train segment. So you have to take care that certain modal combinations which aren't actually possible are prohibited. And one approach that allows for that and also acts as a speed up technique for this basic Dijkstra approach is user constrained contraction hierarchies. So we saw contraction hierarchies in the session on routing and road networks, and the rough idea was that we build a hierarchy of nodes in order of their importance, and we added shortcut edges between them by contracting vertices. And we do the same thing now in each subnetwork, but we take care not to contract edges that are incident to link edges. So, sorry, not to contract vertices which are incident to link edges. So any vertex that is incident to a modal transfer will not be contracted. And what that gives us is that we do not obtain shortcuts that span across different subnetworks. So we do our contraction in the road network until we hit a point where we're only left with vertices that we can contract. Or rather, well, let's be a little more specific. If we say that we don't contract certain vertices, then at a certain point on network or shortcut graph will become so dense that the contraction becomes slower and slower. So we will be left with a small core graph which remains uncontracted, but which is much smaller than the original graph. And we do that for each mode. And because we don't contract vertices that cross subnetwork boundaries, we don't get shortcuts that span multiple modes. And we also restrict the witness search during the contraction to each subnetwork. And so what we end up with is one shared core graph for all modes, and then we have independent subcomponents where we can do CH searches for each mode. And the nice thing about that is that this preprocessing is independent of modal constraints that the user might specify. So let's say we have a user that says, we might have one user that has a private car available, at least for the first leg of a journey. We might have another user that is willing to use taxis, whereas a third user might not want to use taxis. Some users might want to use e-scooters, others might not. So we have different modal constraints depending on the user. And because we do not contract across subnetwork boundaries, this preprocessing is independent of the user specified modal constraints. And now what we can do is to perform a query, we start on the road subgraph and perform a CH query until we reach the common core. And then in the core graph, we run a Dijkstra search, which is necessarily a multi-source, multi-target search, because of course the upward searches will hit the core at multiple different points. And so we do a Dijkstra search between those. And then inside the core graph, there are techniques for taking care of the modal constraints, which I won't be showing you now. But the important thing about this technique is that we only have to do this on the core graph. And on the road subgraph, because we can perform a CH query, we can exploit much faster than we would if we did Dijkstra's algorithm on the whole network. And the search on the core graph is also faster because the core graph is much smaller than the original network. So we get quite a bit of speed up from doing that. Okay, but now we want to leave the world of graph-based public transit modeling again, because as we saw in the previous session, algorithms that are tailored specifically to the timetable are much more efficient. So we're going to be going back to the Raptor algorithm, and now we're going to be looking at a multimodal extension of it, and we're also gonna be looking at multi-criteria optimization. And the entire algorithm is called MCR, which stands for Multimodal Multi-Criteria Raptor. Okay, so our goal is to compute multi-criteria Pareto sets in a multimodal context. We want to optimize arrival time as always, and then for each mode we have mode-specific comfort criteria. So for public transit, we already saw that we need to optimize the number of transfers. And for other networks, we have, for other modes, we have similar criteria. For example, if we allow walking, we should consider walking time as a criterion, because if we don't do that, then we might end up with solutions that are Pareto optimal in the other criteria, but require a lot of walking, and we might miss journeys that are maybe a little bit slower, but require much less walking. And if we allow taxis, then we should include taxi fare and so forth. So if we have a multimodal network, then multi-criteria optimization is basically always necessary, because if we don't take these comfort criteria into account, then the solutions we obtain will be of fairly poor quality. Now there's a problem with that, which is the more criteria we add, the more the larger the Pareto set becomes, because the Pareto set typically grows exponentially in the number of criteria. So for 2 criteria, we were able to do fairly well, because number of transfers is a very discrete criterion, so you only have a few possible values. But we already saw that as soon as we added fare zones into the mix, the number of solutions already got a lot larger. And if we had a 4th criterion on top of that, we will end up with something like that, which is a huge amount of different journeys, which first of all, computing all of these journeys will be very expensive, and just as bad is that if you show all of these journeys to the user, they won't be able to make an informed decision, because there are simply too many different Pareto optimal options. And as we will see in a minute, a lot of them aren't really useful. So let's recap our definition of Pareto sets. We said that the journey J1 dominates the journey J2 if J2 is not better than J1 in any criterion, and a Pareto set is a minimal set of non-dominated journeys. Now, the thing with looking at non-dominated journeys is that a non-dominated journey might offer a minimal improvement in one criterion A, while being much worse in criterion B. So over here we have one solution down here, which includes 1 minute of walking time. And then we have another solution up here, which does not include any walking at all, but its arrival time might be much worse. It might be, I don't know, 30 minutes compared to 4 hours. And that is what we see when we try to minimize walking time in practice, that we end up with absurd solutions that try to avoid walking at all costs, and might be, let's say that your optimal solutions include a necessary walking leg because you might have to walk from the train station to the bus station nearby. And there might be no good solution that avoid this small walking leg, which might be 2 minutes long. If you minimize walking, then you might end up with solutions which go up to the train station, and then to avoid that small walking leg might take a train to another train station, which might be an hour away, but where you can transfer to the bus station without walking, and then enter the bus there and then drive back to the bus station. And that way you get a journey which doesn't include any walking, but is absurdly long. But in terms of Pareto optimality, that journey will be Pareto optimal because it includes less walking. So that's one of the main reasons why, as soon as we add more criteria, we observe a combinatorial explosion. We get an exponential number of solutions, most of which aren't actually very useful. So the question is, how do we identify significant solutions in the Pareto set? And I will show you one possible approach which relies on something called fuzzy dominance. So the idea there is that users typically have a fuzzy notion of what differences in one criterion mean to them. So if you have two journeys which have very similar walking time, and they might differ in walking time might differ by 1 minute, then most users will see that as roughly equal. It doesn't really matter if you have to walk 15 minutes or 14 minutes. But if the walking difference is 30 minutes, then of course that might be significant. So the idea is that users are sensitive to large differences in criteria, but not so sensitive to small differences. And what we do is we relax our notion of Pareto dominance by adapting concepts from fuzzy set theory. So what we do is we define three operators, fuzzy operators, smaller than, equal, and greater than. And usually those would be Boolean operators. So if you have solution A versus solution B, it's either smaller or equal or greater than the other solution. And now we want to make that fuzzy. So we say solution A might be 90% equal to solution B and 10% greater than solution B. So if we look at that plot on the right over there, we have on the x-axis the difference between the solution in our criterion, and on the y-axis we have the degree of equality or being smaller than. So if the solutions are in fact exactly equal, then we would say that the fuzzy equality is 1, and fuzzy smaller than and greater than operators are 0. But as we make the difference between them larger, so let's say the difference between them is 1, then we would say, okay, so it's not exactly equal, but it's about 90% equal. It's still very close to being equal, and it's greater than the other solution by a very small degree, so let's say 10%. And the bigger the difference becomes, the more we shift from equal to greater than, and if we look in the other direction, from equal to smaller than. So we have these fuzzy operators which tell us how big the difference between the criteria actually is, and we can parameterize those operators for each criterion. We can use different parameterizations for each criterion, which tells us how sensitive is our user to walking or to arrival time or to whatever. And then we can define a degree of dominance between two journeys, which is a value between 0 and 1, which tells us how strongly is journey J2 dominated by J1. So if we have only one criterion, then we would we could take this fuzzy smaller than operator to tell us how much it is dominated. So let's say the difference is, I don't know, 10. Then we would say it's dominated by the other journey by about 50%. And then if the difference is 20, it might be dominated by 90%. And if we have multiple criteria, we need to combine these operators for all the criteria. I won't show you the details now, but here's an example of what it looks like for the two criteria, arrival time and walking duration. So we have one solution over here, and the axes show the differences for other solutions compared to this one. So this one is at 0, 0. And if we look at strict Pareto domination, then everything that is above and to the right of this journey would be dominated, whereas everything outside of that region isn't dominated. And what fuzzy domination does for us, it widens the region that is dominated. So this line over here is all the journeys that are dominated, are 98% dominated. So we have some solutions down here which are a little bit better according to walking duration, but worse according to arrival time. And we say, okay, they're not entirely dominated because they are better in one criterion, but the difference is small. So overall, we say it's dominated to a very large degree. And the further away we get from that, the larger the differences between the criteria become, the weaker the degree of domination becomes. So what that gives us is that if we look at the example I showed you earlier, where one journey was much worse in all criteria, but was better by walking time by 1 minute, then if we use fuzzy dominance, we can say that the other journey still 90% dominates journey 2, even though it's slightly better according to one criterion. Okay, so now that we have a measurement for degrees of domination, let me show you how we can identify significant solutions. The first thing we do is we compute the full exact Pareto set with a multi-criteria algorithm, including all those many journeys that we want to filter out. And now we can score each journey in the set with the following score. We compare J to each journey in the Pareto set and compute the degree of domination. So the degree of domination between J1 and J, J2 and J, and so forth. So for each journey, we compute how much does it dominate J, and then we take the maximum of that. So the journey that dominates J the most. And the score of J is 1 minus that degree of domination. So if we have a journey that dominates J entirely, then the score will be 0. And if we don't have any journey that dominates it at all, we will have a score of 1. And journeys that have a higher score are more important because there is no other journey in the Pareto set that dominates it highly. And if we look back to our excessively large full Pareto set, then if we apply that and only show the user the journeys with the highest score, then we might end up with something like that. Okay, so we mentioned that we need a multi-criteria algorithm to compute the full Pareto set, and that is our MCR algorithm, which works as follows. We used the same observation that we already used for Raptor, which is that modal transfers are only possible at certain locations and not within a trip. So each time we exit a trip, we incur one transfer and we can start a new round. So as before, we have 1 round per trip, and we maintain labels at each vertex for each round. And because it's a multi-criteria algorithm, for each vertex and each round, we have a Pareto set of optimal labels, just like we did in the MacRaptor algorithm. And unlike the MacRaptor algorithm, we don't just do that at every stop in the public transit network, we do it at each vertex, including the road networks. And now for each round, we run one sub-algorithm per transport mode. So for the public transit part of the journey, we would run MacRaptor. And for the road-based networks, such as walking, bicycle, taxi, we would run a multi-criteria Dijkstra algorithm, and we can also apply the techniques that we saw for user constraint contraction hierarchies, which is that we can apply partial contraction to the networks to make the graphs smaller, to make these Dijkstra searches a little faster. And then we also perform CH upward searches to get from our source and target locations to the public transit network. And apart from that, it pretty much works like Raptor. So in each round, we will read labels from round I-1 and write labels into round I. And each time we generate new labels, we merge them into the Pareto set of the corresponding vertex, and we remove dominated labels. Okay, so that's fairly simple. Basically, it boils down to alternating between MacRaptor for the public transit part and then multi-criteria Dijkstra on the road network. Now, the problem with the approach as I described it so far is that the queries are going to become very slow. And we're talking about query times of several seconds, even if we only optimize 3 criteria, because I will show you some numbers later, but if we optimize arrival time, number of transfers, and walking time, and we do that on a multimodal network, the number of Pareto optimal journeys becomes huge. We're talking about maybe something like 60 to 70 journeys. And we have to explore the road network as well, so it's a lot more expensive than simply running a multi-criteria Raptor algorithm. So the queries are too slow for practice. So in order to do better, we want to discard journeys that we will later identify as unimportant anyway during the query. So each time we look at a Pareto set at a vertex, we want to filter out journeys where we think, well, they're not gonna end up becoming an optimal or a highly scored solution anyway. And then we want to remove them. And for that, we're going to be looking at a few heuristic approaches. And there are a few types of approaches we can take. One is to relax the dominance rules during the algorithm. And the simplest idea is to take our fuzzy dominance concept and apply it not only after the entire Pareto set has been calculated, but do it between labels during the algorithm. So each time we merge labels into the Pareto set of a vertex, we apply fuzzy dominance there. The problem with that is if we do it at each vertex, this might remove journeys which are fuzzily dominated right now, but might later grow into solutions that won't be fuzzily dominated in the end. So we might discard journeys there that are actually might end up becoming important later. So that's why it's only a heuristic. Another fairly simple idea is to keep strict dominance, but discretize the criteria and slot them into buckets. So, for example, we say each 5 minutes, we don't make a difference between 5 minutes of arrival time or 5 minutes of walking time. So anything between 0 and 5 minutes of walking time is considered equal. Everything between 5 and 10 minutes is considered equal, and so forth. Another idea is to restrict walking. So we have a whole class of heuristics here, which are MCRTX, where X is the maximum number of minutes of walking that we allow between two trips, and RY, where Y is the number of minutes of walking we allow at the source and the target. So we can allow more walking in the initial and final part of the journey than we allow between trips. And finally, we can reduce the number of criteria by merging multiple criteria into one. And one example is to count every X minutes of walking as a trip. And that version we call MRX. Okay, so we want to evaluate the quality of these heuristics, and what we do for that is we consider what we will actually end up doing in practice, which is we use some algorithm A, and then we will present the top K journeys in the Pareto set to the user. So let's say the top 5 journeys or something like that. So we score them according to our fuzzy logic, and the best ones we present to the user. And now we want to match the top K journeys in the full Pareto set to the top K journeys that our heuristics computed, and look at how closely they match the actual top K journeys. So how do we measure the similarity of journeys? We can use our fuzzy equality operator for that, applied to each criterion. And the overall similarity between two journeys is simply the minimal similarity across all criteria. Now, we take the Pareto set computed by MCR, our exact algorithm, as our ground truth, and we say that we only keep the top K journeys in the MCR solution, and also only the top K solutions in the ones computed by our algorithm. And now we line up these top K journeys and compute a maximal matching between them with regard to similarity. So we match each journey in the exact set with the most similar journey in the one computed by our algorithm. And then after we've done the matching, we compare the similarity of the matched journeys, and we output the average similarity of the matched journeys. And the higher the similarity, obviously, the better the heuristic. And if we manage to compute the exact same top K journeys, obviously, that will give us an average similarity of 1. And if we miss out a journey, we're still doing okay if we find another journey that's not exactly the same but similar. But if we don't find a similar journey for one of the top K journeys, then our quality will suffer accordingly. All right, now let's look at some experiments. These were also performed on the London network, which we saw in the last session. Same network basically as far as the public transit part is concerned, but we also added a road and footpath network, which is about 260,000 vertices, which is a lot smaller than the road networks we looked at in pure road route planning. And we also have some bike rental stations in there. Now, first let's look at a scenario without taxis. And we optimize 3 criteria, which are arrival time, number of transfers, and walking time. And our MCR algorithm takes more than a second and computes on average 29 journeys. So if we look back at what we saw in the previous session, we had an average of 9 journeys for the fare zone scenario. So now we have 3 times that, and the running time is much higher. And Yeah, not really applicable for interactive applications. Now, let's look at the heuristics. We have MCR-HF, which applies fuzzy logic during the algorithm, which cuts the running time in half, approximately, also cuts the number of solutions in half, and our similarity quality measure, where we compare the top 6 journeys, gives us an average similarity of 89%. Which is with a standard deviation of 11%. So you do have some deviation in there, but not too huge. Then the bucket version performs even better. We get slightly better running times. The quality is actually higher. And the other heuristics, which this one restricted walking, we have 10 minutes of walking between trips and 15 minutes of walking at the start and end of the journey. And we see that, for one thing, it doesn't actually save that much running time. And the quality is very bad. So we only match the top 6 journeys by 30%. So that goes to show you that restricting walking is actually a very bad idea, because you're going to miss a lot of very good journeys. And as for this one, was combining walking into number of trips as a criterion, and that one is a lot slower because now we're back to just 2 criteria. So basically, it's about as fast as Raptor, but the quality isn't very good either. So these 2 approaches don't work so well, but are heuristics that relax our domination rules achieve pretty good quality. So now let's get taxis into the mix. Now, if we include taxis, we have to add a 4th criterion, because if we minimize walking time, but we don't minimize taxi fare, then taxi always wins and we don't need walking. So we have a 4th criterion. And now let's look at the exact algorithm. We get an average of 1,666 journeys, and the average query time is about half an hour. So that's astronomically high, and we see that indeed the number of optimal journeys grows exponentially with the number of criteria, and 4 criteria are already intractable if we want to compute the whole Pareto set. Now let's look at our heuristics. The one with fuzzy domination cuts that down to 35 journeys and cuts the running time down to 6 seconds, which isn't great, but is at least feasible. And the quality is quite good at 92%, and same quality for the buckets version, and the running time is even better. And now we have a 4th configuration which combines walking time and fare into one criterion. So we define ourselves some kind of a trade-off between walking and taxi fare, how much walking equals how much taxi fare, and get rid of one of the criteria that way. That makes the algorithm even faster. We end up at 1 second, and the quality at 74% isn't fantastic, but still somewhat usable. All right, so so much for multimodal multi-criteria Raptor. We did see some approaches for optimizing multiple criteria, but if we look at the results we've gotten so far, we can't really be satisfied with what we've got, because the algorithms are still fairly slow. So 6 seconds query time is pretty far from interactive. So we do want to do better than that, and in order to show you how to do better than that, we want to look at unlimited walking a bit more closely for a minute. So the public transit algorithms we've seen so far required transitively closed footpaths. That affected both Raptor and CSA, and it also affects most other public transit algorithms. So they do support walking to some degree, but only in a very limited capacity. Because if you have to compute the transitive closure of the footpath graph, then you can achieve or you can represent about 10 minutes of walking with that. And if you go any further than that, then the transitive closure becomes way too large and it's not practical anymore. So the question we want to ask ourselves is, do long footpaths even make a difference in practice? Because many people who come from the more practical side, the people who build these kind of routing applications, what they usually say is, well, that's all fine and good, but we don't really want long footpaths because, for one thing, the users don't want to use them, and for another thing, they don't actually lead to faster journeys in practice. And at face value, you might believe that because walking is so much slower compared to public transit. So why would using long footpaths ever pay off? So we want to study that for a bit. And what we do for that is we take ourselves the Switzerland network, which interestingly is about as large as the London network in terms of the number of stops and the number of trips, even though geographically, obviously, it's a lot larger. And we compare travel times on that network for different footpath configurations. So the first configuration is called original, and that one only includes the footpaths that are specified in the public transit network. So what we did there is we took a GTFS feed of the Switzerland network, and that usually has a few footpaths predefined. But in this case, it's only about 5,000 edges, so it's really only stuff like connecting a train station to the nearby bus station, or maybe connecting different platforms of the same train station. So very few footpaths. Then we have the partial configuration, which includes a transitively closed footpath graph with, I think on Switzerland, it's about 8 minutes of walking. So we connected all stops that were less than 8 minutes apart, and then we built the transitive closure of that, and that gave us about 3 million edges. And then finally, we have the complete footpath graph, which is just the entire OpenStreetMap footpath graph of Switzerland, which actually has fewer edges than the partial graph, which already goes to show you that if you take that approach of building the transitive closure, in the denser regions of the graph, which usually is the bigger cities, you get very large cliques. So all stops within the city region will be connected with each other. And the maximum degree of a vertex here is actually 1,446. So we have cliques of more than 1,000 vertices in that graph. All right, so let's compare some travel times. We took randomly chosen queries on the Switzerland network, once with the complete footpaths and once with the original footpaths. And we did that for a distance rank of 2 to the power of 16. I'm not sure if you know what a distance rank is. It's not that important for what I'm going to show you, but basically you take your source vertex, then you run Dijkstra's algorithm, and then you rank the vertices in the network according to their distance to the source vertex. And then as your target vertex, you pick the vertex with the given rank. And what that gives you is that all the queries we chose have vertices where the distance between source and targets is similar. So in this case, we can see here the green line is the average travel time mapped across the hours of the day. During the day, the average travel time is about 2 hours, and because we chose queries with the same distance rank, the variation between the travel times is not that large. So they're all about 2 hours apart from each other. Okay, so that's the average travel time if we use the complete network with all the footpaths that are available. It's about 2 hours during the day, and naturally it gets larger during the night when the number of available connections is much lower. And especially if you choose random source and target vertices, you're going to end up with a lot of queries which are basically trying to travel from one rural area to another rural area. So especially during the nighttime, you might have to wait a while to catch the next bus. Okay, so this is the average travel time on the original network. And the results might surprise you. The average travel time is 6 hours instead of 2. So it's extremely bad. So that goes to show you, if you leave out walking altogether, then you're going to end up with very bad travel times, because basically what that means, if you start at a random location, you might start at there might be another bus stop nearby which actually travels in the direction you want to go in, but you can't walk there because there is no edge between them. So you have to take absurd detours to actually end up at the bus stop where you wanted to go to in the first place. So not including footpaths, or only including those footpaths which are supplied in the network itself, is not enough. Now, some more statistics. The median travel time difference between the two is about 1 to 2 hours during the day. It gets larger during the nighttime. So most queries are affected. Some are affected very heavily, some not quite as heavily, but still with an average travel time of 2 hours, the travel time difference of 4 hours is very bad. This is the interquartile range, which is probably not that important. Here, the dotted line, you see the percentage of queries where the travel times differ between the two configurations, and it's close to 100%. So almost every query is affected. And the percentage of queries where the travel time difference is greater than 1 hour, as shown here, and that's also always more than 50% and even higher during the nighttime. I saw a question there. The question was, isn't this more of a problem with choosing completely random OD pairs instead of more reasonable combinations? Certainly. I expect that the difference will be much smaller if you choose reasonable combinations, but you have to keep in mind that what we're doing here is multimodal route planning. So right now in the original network, we don't actually have anything in the graph that gives us locations that are outside of the public transit network. So all these queries actually already start at a stop in the network. So it's not like we're starting at some road somewhere somewhere in the middle of nowhere. So we are starting at actual public transit stops. So we would expect that we do have some, so we are connected to the public transit network. And as you can see, this affects more than 50% of our queries. So even though I would expect the differences to be smaller if we choose realistic queries, we would still get a lot of queries where the difference is large. Now let's do the same experiment with the partial network. Now let's switch back just to compare the two. So we can see that the difference shrinks considerably, and well, that's probably not as surprising, because now we no longer have the problem where we start at one station and we can't get to the next one, even though that would be a more reasonable place to start. But we still observe a difference in the travel times, and it's not that large during the day, but it gets larger starting in the evening and even larger during the night. And the percentage of queries that are affected is about 25% during the day, a little bit more or a lot more during the night. And there's still a lot of queries where the difference is greater than 1 hour. So by using this partial network, we're probably going to answer a large percentage of the queries reasonably well, but there will still be quite a few where the solutions we get aren't of acceptable quality. So we want to analyze that even more closely now. So we want to ask ourselves which parts of the journey actually require unlimited walking. And we're going to classify the types of transfers that are possible. We have initial transfers which connect the source vertex to the first trip of the journey. So this one, final transfers connect the last trip to the target vertex, and then we have intermediate transfers which connect two trips to each other. So we exit one vehicle, walk to another stop, and then enter another vehicle there. And our hypothesis is that long footpaths are mainly necessary during initial and final transfers. So they are necessary in order to connect our source and target location to the public transit network and actually start at the station where it makes sense to enter the public transit network. And by contrast, long intermediate transfers we expect to be much less common, because if it's necessary to walk 40 minutes in order to improve your arrival time, then probably a public transit network isn't built very well. So we did another experiment with a new footpath configuration we call partial intermediate. We allowed unlimited walking only for the initial and final transfers, and then for the intermediate transfers, we switched to the partial graph. And then we compared that to the results for the complete graph, and up. There we go. This is what we got. So the travel time difference has been reduced to almost nothing on average. The two lines are very close to each other. The percentage of queries where we get a difference at all is about 10 to 15% on average, and the percentage of queries where the travel time difference is greater than 1 hour is almost zero. So that confirms a hypothesis that initial and final transfers are important and we shouldn't restrict them. And long intermediate transfers aren't usually that necessary. So the set of intermediate transfers that we need at all to answer queries correctly is probably quite small. Okay, but of course it's not zero, and there are still examples of queries where we need intermediate walking to improve our arrival time, and the intermediate walking leg is longer than, say, 10 minutes. So this is a real world example. We start in a town called Geislingen an der Steige, and we want to travel to Ulm Hauptbahnhof at 13:10. And we have two journeys here, which, as you can see, are almost identical for most of the journey. So this is, I think, an IC to Ulm. And the difference is mostly within Geislingen. So let's zoom in a bit. And this is our source location. And we have two train stations, Geislingen West and Geislingen an der Steige. This is the result we get if we allow unlimited initial and final walking, but we limit intermediate walking. We get a walking leg. It takes about 26 minutes to Geislingen an der Steige, and then we take the train that arrives in Ulm at 14:48. And now let's allow unlimited intermediate walking. And now what we can do, is we can take a bus from here to the middle of the town and then walk about 20 minutes to Geislingen West. And now we arrive early enough to catch an earlier train, and we arrive at 14:01. So this is an example where a fairly long intermediate walking leg is in fact useful. And you can imagine that if you allow a faster transfer mode than walking, let's say you have an e-scooter available or something like that, then these kinds of examples get more frequent. Okay, now I want to show you a technique which I have to apologize again, is called Ultra, which stands for unlimited transfers. Yeah, and it gets even worse as far as naming is concerned in a minute. But for now, let's recapitulate our problem setting. We are given a public transit network which models all schedule-based modes of transport, train, tram, bus, and so forth. And we have an unlimited transfer graph. And to make it a bit easier on ourselves, we only allow one non-schedule based mode of transportation. That can be walking, can be cycling, e-scooter, and so forth. So just one extra mode, which we call the transfer mode. And now we have our usual earliest arrival problem. Well, not quite earliest arrival problem. We have a source vertex and a target vertex and a departure time, and we want to compute a Pareto set according to arrival time and number of used trips. We restrict ourselves to these two criteria for now. So what do we want to do? We saw that pure public transit algorithms can only handle limited transfers, and so far our only alternative to that is MCR. There's a variant of that which only has two criteria, which is called MR infinity, because it goes back to that MRX heuristic where X minutes of walking counted as a trip, and we set that to infinity, so walking never counts as a trip. And that's basically a two criteria variant of MCR. And that needs expensive Dijkstra searches on the road network to explore the transfer mode, so it's much slower than Raptor. Now, our goal is to allow for unlimited transfers without any performance loss during the query algorithm. So we want to get back to the fast performance of Raptor, but allow unlimited transfers. And obviously we don't get that for free, so we have to allow ourselves a pre-processing phase in advance to compute some information that we use during the query. Now, what are our conclusions from the experiments which we just looked at, which is that unlimited walking often pays off, at least for random queries. And another point that might be relevant in that regard is that if we come at things from an algorithmic perspective, we're usually not satisfied with saying, okay, we might not answer every query correctly, but we answer realistic queries reasonably well. So we do get worse travel times on some queries, but on most realistic queries, we're doing fine. Where in our context, we're not satisfied with that. We want to answer every query correctly. And so that's going to include queries which start from fairly remote locations and end at other fairly remote locations, which might not be requested that often, but still some users might have those kind of might want to take those kind of routes or need to take those kind of routes, and we still want to answer their queries exactly as well. And of course, everything I showed you so far only goes for unlimited walking, and it's natural that if you allow for a faster transfer mode, such as cycling or e-scooter, the impact of unlimited walking will, or in that case, unlimited transfers, will only increase. The other thing that our experiments showed us is that we have to treat initial and final transfers differently from intermediate transfers, because initial and final transfers, actually let me skip to the next slide, because there's a small list of pros and cons there. Initials and final transfers are frequently necessary to answer queries correctly, and they are often long in those cases where you start in a remote location and have to transfer to the most suitable stop. As for intermediate transfers, they are rarer, and when they do occur, they are mostly short. So we might transfer from one station to a neighboring station, but we probably in most cases won't be needing to walk across town or even walk to a nearby town between two public transit trips. The advantage of initial and final transfers is that we already know one of the endpoints, because it's either a source vertex or a target vertex. In the case of the intermediate transfers, we don't know the endpoints in advance, because as we explore our network, we end up at a lot of stops, and then from each of the stops where we end up, we need to consider the possibility that we might want to transfer from there to any other stop in the network. And any combination of stops might technically be important. So we don't know the two endpoints in advance. And this is a difference we can exploit algorithmically, because there are techniques on road networks for answering so-called one-to-many queries, where we have one fixed endpoint and a larger set of possible destination points. One of the techniques, which is quite fast, is called bucket CH. So that's an adaptation of contraction hierarchies for one-to-many searches. And we can use that here by performing a one-to-many search where the one fixed vertex is our source vertex and the many target vertices are all the stops in the network. And on a network like Switzerland, we can compute shortest path distances from S to all vertices, all stops in the network in about 1 millisecond. So we can answer that quite quickly. And we can do the same in reverse for the final transfer. So that gives us, in a very short time, all the possible options for the initial and final transfers. So even though there are a lot of options, we can compute them all quickly. Now, for the intermediate transfers, we can't do that because we don't know the two endpoints, but the advantage is that there aren't as many options. So what we do is we pre-compute shortcut edges for all intermediate transfers that will be relevant in any possible query we might perform. So for each intermediate transfer that might ever be necessary, we include a direct edge from the one stop to the other stop that we transfer to. And then during the query algorithm, we have direct edges. So we only have to do to relax the outgoing edges of each stop and achieve transfers to other stops with one hop in the shortcut graph. I think we're a little short on time, so I probably might need to skip one or two things, but I will explain to you the basic idea of this preprocessing. So if we do it very naively, we would enumerate all Pareto optimal journeys in the entire network for all possible source and target vertices and for all possible departure times. And then for each Pareto optimal journey, we could insert a shortcut every time it uses an intermediate transfer. Now, obviously, enumerating all Pareto optimal journeys in the entire network is very expensive. So we don't want to do that. But we can start from that point and then slowly try to add some optimizations onto that, so we don't have to do quite as much work. And the first insight which we can use is we can exploit the so-called subpath property, which is that subpaths of optimal paths are also optimal, at least if you restrict the selection of subpaths that are allowed. So in the case of public transit, we can say that if we only enumerate journeys with exactly 2 trips, then from those optimal journeys with 2 trips, we can build every other journey that includes more than 2 trips. So that's the first optimization, which is we can restrict ourselves to exactly 2 trips. And the nice thing about that is that if we only have 2 trips, we also only have one intermediate transfer between those 2 trips, which we need to look at. Okay, so a naive implementation would basically use MCR, or rather MR infinity for our 2 criteria, limit that to 2 rounds, and then perform a profile variant of that. So we don't have a fixed departure time, but we want to find the optimal journeys for all possible departure times during the day. So for Raptor, we saw we looked at the R-Raptor algorithm, which solves profile queries for pure public transit. And we can do something similar for MCR. And so we do that for each source stop and perform profile searches to all other stops for all possible times of day. So that's still very expensive, but since we limit it to 2 trips, it's already not as expensive as it used to be. Now there's a slight complication there because if we perform a naive profile search with MCR, it's going to be very slow. I will go over this one fairly quickly, I think. If you remember how R-Raptor worked, we said that we take all possible departures at the source stop, and for each possible departure time, we do 1 Raptor execution. And then we do those in order by decreasing order of departure time. And because at each stop there aren't that many possible departure times, it's not that many Raptor executions that we have to do, and that's why it's efficient. Now, if we allow for unlimited walking, the problem is that we can start at our source station and walk anywhere we want to. We could walk from here to Hamburg and start there. And we don't know in advance if that will be necessary or not. So we don't actually only have to look at the departures of vehicles directly at our source station, but we have to look at all departures in the network that are possible. And we have to do 1 for each possible departure time, which is way too much. Fortunately, we can do better than that because we don't have to enumerate all Pareto optimal journeys with 2 trips. We only need to enumerate enough so that we find all intermediate transfers that are necessary. And so we classify journeys into 2 categories. One is candidate journeys, which have the form a trip followed by an intermediate transfer followed by another trip, but no initial and no final transfer. And then witnesses are all other journeys with up to 2 trips. So this one has a final transfer, for example. Here we have another one which doesn't even have 2 trips. Here we have one that consists only of walking. All these kinds of journeys are called witnesses. And now the fundamental insight is that if a candidate is dominated by a witness, then we don't need to represent the intermediate transfer that the candidate uses with a shortcut, because we can always take out the candidate and replace it with the witness instead and still get an optimal journey. But if we have a candidate where we don't find a dominating witness, that means that we do need the shortcut. So what we do is we try to enumerate all candidates, and for each candidate we try to find a dominating witness. And just to quickly explain why that solves the R-Raptor problem, candidates don't have an initial transfer, so we can go back to what we did before, which is do one Raptor execution for each departure time at the source station, and then we need to find for this departure time all the candidates that start with this departure time, and then if there are witnesses that dominate this candidate, we need to find them as well. So let me skip this one. We do have time for a very short overview of how the algorithm works. So for each source stop S, we perform our profile search. We can do this in parallel very easily. We relax the initial transfers from S to all stops. We collect all possible departure times. And then for each departure time at the stop in descending order, we perform a Raptor execution, which collects and scans initial routes. Then it relaxes intermediate transfers. This is the first round. Then we do the second Raptor round. We scan the final routes. And once we're finished with that, we have found all possible candidates that might exist, because candidates don't have a final transfer. And then we relax the final transfers, which won't find us any more candidates, but might find witnesses that dominate existing candidates, so we can prune further candidates with that. And then once we're done with that, we can look at each candidate that still remains that wasn't dominated, and for each one unpack the intermediate transfer and insert a shortcut for it. All right, so that's the pre-processing for the intermediate transfers. And now the query algorithm, we compute the initial and final transfers with a one-to-many algorithm. I already talked about that earlier. So these are the initial transfers from S to all the stops. We can view them as a set of shortcut edges from S to all the stops. The same from all the stops to T. And now we have the pre-computed intermediate transfers, and now we add all of those together and route on this resulting network. And so just saw a comment in the chat, but that doesn't concern this talk, so let's continue. This graph might not look any simpler than the one we started out with, but the advantage is that we only have to explore the initial transfers once, and then initialize all the stops that we reach with their respective distances. Then we can run on the public transit network any query algorithm of choice using the pre-computed shortcuts. And then we can integrate final transfers, which is done by every time we arrive at a stop, we check if we can take a final transfer to the target and improve our arrival time there. All right. We have about 10 more minutes, which is probably enough to go over the experiments. This is on the Switzerland land network with 16 cores, and this is the shortcut computation. And the x-axis shows you the transfer speed of the transfer mode that we use. So we have, for walking, we used 4.5 kilometers per hour. And so here we got a preprocessing time of about 10 minutes on the Switzerland network to compute these shortcuts. And we see that the preprocessing time rises for higher transfer speed. So here we have a maximum of 18 kilometers per hour, which is well, probably a bit faster than what you would be than what you would achieve with bicycle or e-scooter. And from there on, it gets faster again. As for the number of shortcuts that we obtain, for walking, we get slightly below 150,000 shortcuts. So if we remind ourselves what we had on the Switzerland network for the unrestricted graph, we had about 1.8 million edges, and on the transitively closed network, we had about 3 million edges. So we were able to cut that down by about a factor of 20. And once again, that shows that intermediate transfers might be relevant in some cases, but the number of different transfers that are relevant is not that high. It's about 150,000 that could ever possibly be relevant to answer a query. Now, the number of shortcuts rises as the transfer speed rises, which is unsurprising because the faster you can transfer, the larger the distance you can travel. And so we get a small peak there for 16 kilometers per hour, which is about biking speed. And then we see something very interesting, which is that the number of shortcuts declines. And we looked at two configurations. One is one where we obeyed the speed limit of the network and one where we ignored it. So this means that if we have 100 kilometers per hour, we assume that we can actually drive 100 kilometers per hour through pedestrian zones and any kind of road. So it's not very realistic, but it's just to show you what happens if the transfer mode becomes very fast. So we had hit a plateau here at about 140 kilometers per hour. And if we obey, that's if we obey speed limits. If we ignore them, it starts, it actually declines. And so the reason for that is if the transfer speed becomes very fast, then you never have a reason to use public transit anymore, because you're always faster if you simply use the transfer mode to get from source to target. So actually what we should be expecting is that the number of shortcuts declines to 0. And the reason it doesn't is because there are stops in the transfer in the network that are isolated in the transfer graph. They don't have any outgoing edges into the transfer graph. And so if we filter out these stops, we see that the number of shortcuts declines because stops that are isolated in the transfer graph don't have a solution that doesn't use public transit. Don't have a solution that doesn't use public transit, so we always get an intermediate transfer somewhere. But if we filter them out, we see that the number of shortcuts declines to 0. So ultra is practical for any kind of transfer speed because the number of shortcuts remains low. All right, now for query performance, ultra can be combined with any public transit algorithm, and the one I'd like to show you is the combination with Raptor, which, again, I'm very sorry, it's called Ultra Raptor, and we compare Ultra Raptor to MR Infinity, which is the fastest approach that existed before, and we see that the overall query time is reduced by about a factor of 2 on both networks. And if we look at the detailed running times, we can also see why. We have here the time for the initial transfers, which is 11.6 milliseconds for MR Infinity, but only 1.6 for Ultra Raptor, because we use a fast one-to-many technique. We have the time for collecting and scanning routes, which remains about the same, which obviously we couldn't expect to make any improvements there with our technique. But the time for relaxing the transfer graph is reduced significantly from 12.3 to 1.9. And overall, if we compare it to Raptor on a transitively closed network, we see that we achieve about the same running time. So it's not just faster than a factor of 2, by a factor of 2 compared to the state of the art. It's also about as fast as we could reasonably hope for, because we reduced the impact of the transfer graph to about 20% of the overall query time. So now the time for exploring the public transit network dominates the running time. Okay, and I think we can make this slide very short. This shows you the query time for different transfer speeds. So the last slide was only for walking, but the speed up remains in place for higher transfer speeds as well. And in fact, the overall query time declines both for our baseline algorithm and for Ultra Raptor as well. And the time spent relaxing the transfer graph is about 50% for MR Infinity, and it shrinks to about 10 to 20% for Ultra Raptor. Okay, that's about it for multimodal route planning. So just a quick outlook. We're still working, or we have been working over the past 2 years on extending the Ultra approach further. One thing is that so far we only optimize 2 criteria. So we want to extend that to more criteria and also to more and different transfer modes. We already looked at bike sharing stations. Another quite important thing that we're working on is, so far the pre-processing assumes that all the trains run on time all the time, which obviously is not realistic. And we want to expand the shortcut computation so it can handle delays. Right, and we also applied Ultra shortcuts to a variety of scenarios, including multimodal traffic assignments, one-to-many queries. We also adapted it for other public transit algorithms. But yeah, this is still an open area of research. All right, so that's it from me on multimodal and public transit routing. I hope it was informative, and if you have any questions, yeah, you can ask them now.